the overall Hamiltonian function of the system is just sum of all momenta squared divided by 2 plus sum of all potential functions of the sort. So reportedly this system actually was first observed in the famous numerical experiment of Fermi and Ulam in 1950s, where it was noticed that this particular choice of potential gives you some very weird non-chaotic behavior of the points. So non-chaotic behavior meant that this system is in fact integrable. That was the conjecture, but the official start of the history of the system was 1960s. It was soon observed that this particular system is in fact integrable in the simple Liouville sense. That is to say, there exists a sufficient number of first integrals in involution, and to see that these integrals actually exist, Flaschke, I think it was Flaschke who introduced this observation, found the following lax form of the system. You can do the following coordinate change, introduce bi equal to
recording in progress.
Oh, I see. Pi divided by square root of 2, and ai equal to sorry. Can you check the sound? Otherwise we shall have problems. And now, они независимы на самом деле. Эти два передатчика независимы. Этот передатчик, он идет только для... Do you hear me now? Strange. Okay, so AI, they're just E exponent of 1/2 Qi minus Qi plus 1, so that H is just sum of the squares Bi plus AI, right? And in this case, the system, which is given by, so does it work? Oh, sorry. Yeah. У меня есть какая-то, видимо, черная аура для интернета. Если я прихожу, все что-то ломается. Часто. Это, видите, это моя, видимо, аура.
Это единственный потенциал, при котором интегрировалось есть?
Я не знаю, но это просто конкретный потенциал для системы Тоды. В принципе, вообще, ну, как бы это сказать, вопрос такой, который, конечно, там много всего в разных системах есть. Я не помню, значит, получается, в принципе, если мы возьмем полную симметрическую Тоду, то получится, что есть и другие потенциалы. То есть, например, полная симметрическая, там как бы можно, видимо, написать Ферми. Но это как бы я не видел, что вы занимались.
Что, можно?
Are we going on?
Ну, оно все равно ломается, так что...
So it's currently breaking and repair. Okay, let's proceed. In spite of all odds, okay. So we have this potential function, and in the usual way we write down, the usual way to write down Hamiltonian system is to say that P dot is equal to dH dq, and Q dot is equal to dH minus dH dP, minus dH dP. So the same can be done here in these new coordinates, and in these new coordinates one can see that actually the corresponding vector field can be encoded in the following Lex form. You consider the Lex matrix L, just symmetric matrix with 3 non-zero diagonals, 1
Recording in progress.
central diagonal, B1, Bn, and 2 off-center diagonals, A1 through An minus 1, A1 through An minus 1, right? And all other entries of this matrix should be 0. Then we can anti-symmetrize this matrix in a very naive way. Just write down M of L equal to zeros on the diagonal, A1 through An minus 1 above diagonal, and minus A1 through An minus An minus 1 above diagonal. All the other elements are 0. Then the system, this sort of system, is equivalent to the following Lex form. L dot is equal to the commutator of M, L, and L. So that was the start of the sort of system. And in this form, it is easy to see that there exist sufficiently many functions which commute with the Toda flow. For instance, you can take traces of the powers of M of L for k from 1 to n. All these functions will definitely be invariant with respect to this flow, just because the trace of the commutator is equal to 0, right? It is a little bit less easy to see that these functions will commute with respect to this standard Poisson structure, symplectic structure. That is, when pi commutes with qj by delta ij. But it still can be done. And in order to see this, sorry? In order to see this, one can, for instance, do the following thing. Suppose you have a function f of entries of the matrix L, and it turns out that the Hamiltonian vector field of M x sub f, the Hamiltonian vector field of F, will be equal to the anti-symmetrization of the gradient of the differential, call it as you want, of the function f. So the gradient of f will be 3 diagonal matrix. You can interpret the gradient of f as a 3 diagonal matrix, just matrix of partial derivations of f with respect to the
just apply this n to.
Just apply to this, and this will be. And if you use these observation, then you can actually prove that these functions will not just commute with the Toda flow, but they will commute with each other as with respect to the Poisson structure. So that is the traditional, the usual, what they call open Toda chain. Since that time, in 1960, when the Toda flow was first discovered, there have appeared lots of various generalizations of Toda system. These generalizations are usually obtained by considering some special kind of Lex matrices instead of 3 diagonal matrices, symmetric 3 diagonal matrices as we do here. One popular way to consider to do this generalization is the following, which I'm going to talk about. It is just take L to be arbitrary symmetric matrix. And use the same anti-symmetrization procedure on L. Just delete the diagonal, preserve the sign above the diagonal of the elements above the diagonal, and change the sign of the elements below the diagonal. So a 1n. So of course I sorry I forgot to
Recording
say
in progress.
that of course aij is equal to aji here. And then use the same formula to define the total flow. This generalization is
Gosh, was it assumed in the beginning that L is symmetric?
yeah. Sorry, yeah, it is symmetric. Actually, one can do this with more general matrices than that.
But now it,
Yeah, but for me, at this my talk, it will be this. Actually, there are other choices. One can consider so-called Hessenberg matrices, where a certain number of central diagonals are non-zero and the rest are zeros. One can consider periodic total flow, that is to say, a three-diagonal matrix plus elements here and here in the corners. That's what they call periodic total flow. One can consider full constant total flow, where the matrix looks like this. You have lower triangular matrix and units above the diagonal, and zeros elsewhere. So there are lots of different generalizations, including the generalizations to some other Lie algebras. One can actually take more or less any semi-simple real Lie algebra, and it will give you a total flow on this semi-simple Lie algebra. And in general, one can ask what choices of matrices you can do to obtain this kind of closed equations. And I think this spring I refereed a diploma thesis of a student from High School of Economy who classified all possible choices of matrices for which this kind of equation is well defined. Yeah. So there are lots of possible generalizations, but which is really interesting for us, it is that all these generalizations, at least this generalization, and all the other generalizations which I have mentioned, well, except I don't know about these new generalizations found by the student, but all these other generalizations, they are actually also Hamiltonian systems. So I'm interested in this full symmetric total system. So for us at this talk, the next matrix will be a generic symmetric matrix. M of L will be its naive anti-symmetrization, and the equation which we are going to consider is this: L dot is equal to M of L, comma L. Now this system is Hamiltonian, and to see this, one needs to consider the direct sum decomposition of the matrix space. Let me do it like this. We have matrix space, and it is equal to the symmetric part and anti-symmetric part plus anti-symmetric part. Right? So anti-symmetric is a Lie algebra of special orthogonal group, so I write it like this. And you actually can even say that on the left we have SLN or GLN if you prefer. Up to you. So now we can use, so SLN is probably better because SLN is semi-simple and you can use a killing form to dualize this picture. And when you dualize, you see that SON dual is SON, more or less, right? Because it's both negative and definite, right? And symmetric n is isomorphic to Bn star. So this isomorphism now allows us to pull the classic, the canonical Kirillov constant Suryo.
What is Bn?
This is the Lie algebra, Borel Lie algebra of upper triangular matrices. It's actually either upper triangle or lower triangle. It doesn't actually matter. Yeah, because the dual decomposition is that.
Recording in progress.
Sorry. Yeah, so now it means that we have a Poisson structure on symmetric matrices, which is induced from Bn star. And naively speaking, it just means that we forget about, say, lower triangular part of symmetric matrices and identify the remaining part with Bn star and use this identification to pull the Poisson structure from dual space of a Lie algebra to symmetric matrices.
So here we have it because SON is
Self-dual.
Self-adjoint.
Yes, yeah.
And here
Yeah, so it is just orthogonal. This is the orthogonal complement of SON, right? It's just actually you don't even need to go into these depths in this definition. It is sufficient to use this identification I mentioned at the end. But this identification can be used for different choice of Lie algebra. If you have a real Lie algebra, this decomposition is what they call the Cartan decomposition. And then you can use the Killing form to identify this part of Cartan decomposition with the dual space of the Lie subalgebra. But in the other case, you actually don't need to remember about this. Just use this naive identification. And so if you use this identification to introduce the Poisson structure on the symmetric matrices, then if you choose the Hamilton function equal just to the trace of L square, then this system will be Hamiltonian system with respect to this Hamilton function. This is just a standard result from this theory. And of course, in this case, the commutative family we have just described, trace of L to the power k, will still remain commutative family of functions of first integrals of this Toda system for the same reasons, just for the same reasons. However, this family is not sufficient now because the number of functions here is, well, n, or n minus 1 if you throw away the Casimir function, which is equal just to the trace of L, right? So the number of functions is n or n minus 1 if you throw away the Casimir function. But the dimension of the space of symmetric matrices is proportional to n squared. It is actually n times n plus 1 divided by 2. So the dimension is much greater than the number of functions that we have here. Well, unless n is small, of course. So the integrability of this system, in the Liouville sense, and when I say in Liouville sense, it means that we need to choose suitable symplectic leaves inside this Poisson manifold and find sufficiently large number of first integrals and involution on these leaves, independent first integrals and involution on these leaves. So the number of, so we need to find the, well, remaining n minus 1 divided by 4, I think, something like that, number of integrals. That's how many integrals we need to find still about this. And it is a little bit surprising that actually these integrals can be found, and these integrals, not just integrals, but integrals in involution can be found in this case. There are, I don't know, there are different popular ways to introduce these integrals. So I'll stick to the most popular one, which is called the chopping procedure. And it was found, described first in 1986 by 4 authors: Dave, Lee, Nando, and Tomei. And it consists in the following pretty peculiar construction. So we need to find a sufficiently large number of first integrals and involution of this system. And we need to, and to do this, we consider the characteristic polynomial of L. So when you just take the characteristic polynomial, you barely get something equivalent to the collection of traces of the matrix, right? The functions that you get, they'll be invariants of our space of matrices, and they will be equivalent to the functions you obtain by taking traces of the powers of L. Nothing new. But what you do here to enhance the number of functions, you do the chopping of this matrix. So what is it chopping? You take the matrix A11 minus lambda, A12, and so on, A1L, A12, A22 minus lambda, and so on, A2n, and so on until you get to A1n, ANN minus lambda, and then you delete the first k rows of this matrix and the last k columns of this matrix. What remains will be a matrix of size n minus 2k times n minus 2k, which will still depend on lambda unless 2k is greater than n.
Why 2k?
Because you throw away here and here.
Yes.
Sorry. Yeah, n minus k, right. N minus k times n minus 2k is the degree of the polynomial.
Yes, that's right.
Because you throw away k lambda in this part and k lambdas here, right?
That's right.
Yeah, so the dimension of this matrix will be, right, n minus k times n minus k, but the degree of the polynomial, which is will still depend on lambda, will be n minus 2k.
That's right.
So you write down this polynomial as the function of lambda. Right? And then if you take Aik j of L equal to the ratio of Ekj of L by Ek0 of L, then these functions will be invariants of the total system, will be first integrals of the total system, but they also will commute with each other with respect to the Poisson structure on symmetric matrices. This is a rather unexpected result, I would say. The construction is very, very unusual from the point, well, it's something you really rarely see in the study of integrable systems. So, but you know, the original proof was given by very straightforward and, well, complicated computations by induction. So the first thing I'm going to prove now is that I'm going to prove that these functions are in fact give you a commutative family of first integrals of the system. Of course, this is not something very new, because you know I told you that this has been proved by Dave, Lee, Nanda, and Tamei in 1986. But I'm going to give you a very, in my opinion, nice and streamlined proof of this fact without any computation whatever, almost no computation at all.
And the number of these
integrals
is sufficient?
Well, you see, there are, now you have two indices, k, which goes from 1 to, well, I think to n over 2, because when n is greater, when k is greater than 1/2 of n, there are no such integrals, right? So there are, k goes from 0, well, 0 is not interesting, 1 to integral part of n over 2, 1/2 of n. And j goes from 1, from 0 is not interesting, 1 to k. To again n over 2, I think, right? Yeah. Sorry. No. To n minus 2k. Yeah. So you see the overall number is quadratic. So the total number will be proportional to n squared divided by 4. That's more or less as much as we need. And actually one can compute the total number and do it very carefully and show that, well, on symplectic leaves, if you just count the number of first integrals and the number of Casimirs, and they will match. So that on symplectic leaves you will have Liouville integrability. Yeah. Okay, so I'm going to talk about the
And what is the codimension of?
Huh?
What is the codimension of the generic?
I think that the maximal leaf will be more or less of the same dimension as the space. It's, as far as I can remember. You don't have the drop of dimensions on maximal leaf. Yeah, sorry. No. Yeah, sorry. No, you have, but I mean, there is one Casimir which is just given by the trace of L.
Yeah.
The trace of L is one Casimir, but otherwise than that, I think for the generic n, I don't think there are many others for generic n. In some small dimensions, for instance, in n equal to 4, there are other Casimirs as well known. One of them are rational, as far as I can remember. But yeah, I think this is it. And the reason for my belief in this is that actually, the dynamics of total system is dynamics on the flag manifold. And moreover, this dynamic is concentrated on Schubert cells of flag manifolds. And maximal Schubert cell is symplectic leaf. That's yeah, usually and this maximal Schubert cell usually has the dimension of the flag manifold itself. Yeah. Yeah, I need to check this, but still the number is proportional to n squared divided by 4, and that's more or less as much as we need to ensure the integrability. Yeah, and yeah, but some of them might be, but in some cases, for some particular choice of n, some of these first integrals might be Casimir's, in fact. Sorry, but I don't remember which. Sorry for this. I think Yuri Chernikov knows this best of all of us. So I'm going to prove the commutativity of this family. So this commutativity is based on the following trick known as the Adler-Kosten-Sims scheme. Suppose you have a Lie algebra G, and you can decompose it into direct sum of G0, G1, and G0 and G1, which are Lie subalgebras. And suppose now you have a decomposition of the symmetric algebra of G as a direct sum of two Poisson of two subalgebras closed with respect to the Poisson Poisson bracket, right? That is S of G0 and G0, G1 S of G. Right? You have this. Right. I think if I don't use brackets, parentheses, no need to use it here. Now, if you have F and G in SG, and you assume that F and G are invariant with respect to G0, and such that F and G commute. I think this is sufficient. If not, I might also assume that F is in the central, but I don't think it's necessary. Then their projections onto the first component will commute with each other. I just put it like this: F1, F0 will commute with G0. The proof is very straightforward and just one line proof. Just look into the commutator of F0 and G0, and this is equal to F minus the opposite side, F1. Yeah. Am I right? Sorry. Just a moment. I need to check this. Okay, just to make sure I'm not making. It seems that, yeah. Just a moment, I need to check this in my writing. Here it is. Here it is. Yeah. Yeah. Yes. Yeah. Okay. So just write it down. Yeah, that was correct. And probably better to begin with F1. Sorry. Yeah, that's the only thing which makes it better. Okay.
What is so?
I-
Zeros are projections to,
Yeah.
to the first.
To the first
Sum.
component, yeah, to the first summand, and ones are projections to the second
And
summand.
once
Yeah. To
so
the,
we take F and G and the commutative of projection.
Yeah.
Yeah. Okay.
yeah. So now, what is this? So we have f comma g, which is 0 by assumption, plus, or probably minus, f g0, which is 0 because g0 is from this algebra,
Yes.
and we assume that f was invariant with respect to g0.
Yes.
Similarly, f0 g is equal to 0. And what remains is just f0 g0. Right? So we have f0 g0, but on the other hand, this belongs to the first component, and this to the second, but they are complement to each other, complementary to each other. So we see that both sides of this should be equal to 0. But for us, the most interesting part is this. As you see, of course, we don't even need to work with polynomials. We can actually work with rational functions. With rational functions, if we have rational functions of g, we can also do the same kind of decomposition. And under the same assumption, we shall have the same result. So if you have rational functions f and g, rational functions of g, which are invariant with respect to g0, then their projections to the rational functions of g0 will be equal to just to this. We'll commute with each other. Okay. So now we are only interested in finding rational functions which will commute with each other. Rational and invariant with respect to g0. For our purposes, we shall take the following decomposition of SLN. It will be equal to the direct sum of Bn lower triangular matrices, or probably upper triangular matrices. So upper triangular matrices here. Yeah, upper triangular matrices. Plus SON. So this will be G0, and this will be G1. And the claim is that this ikj of L equal to, so let L now be an element actually in SLN. That is to say, we have a matrix, arbitrary matrix with 0 trace. The only condition we have that 0 trace is 0. Then we shall say that ikj will commute with each other for all k, j, p, and l. And for all kj, ikj of L is Bn plus invariant. So we now have, if this is proved, then just by this AKS scheme, we have the commutativity of the Chopin integrals. So, in order to prove this, there are different ways to prove this. Well, one can do this by direct computation. That's actually what Nanda, Lee, and Tamei and others did. Dave, Nanda, Lee, Tamei. One can actually derive the same result from the general properties of Gaden systems. This was done by Dima Talalayev about 10 years ago in a paper where he even tried to quantize further this system by passing to universal enveloping algebras. So I'm going to derive this observation from a very simple, derive this result from a very simple observation. Namely, I'm going to prove the following very interesting, well, in my opinion, claim. Consider the following system of nested parabolic subalgebras in SLN. So SLN for me will be P0, and then there will be P1, and so on until we go to Pn, which is just 0. And what is Pk0, Pkn? It is the subalgebra of matrices with zeros spanning along the first k rows and the last k columns. So, of course, when you take two such matrices and take their commutator will be of the same form. Is evident, right? So we have this nested family of Lie algebras.
But why are they in SLN?
I mean, take SLN and take all matrices inside SLN, which have zeros here and zeros here, just this.
But you change the trees when you...
Yeah, but I didn't say that it's not projection. I do not just project there. I do not just project. I just take the inclusion. One subalgebra is in. But if actually, I can forget about this and just speak about SGLN. The difference will be just that. I didn't speak about projection. I didn't speak about projection. I said that you can take subalgebras inside SLN which have this form. Right? But if you don't like this, it's probably easier to work with GLN. Yeah. Just safer, right? Then, but the claim is the following. Claim. Take E Km of L, the coefficients of the characteristic polynomials of the Chopin matrices. So you remember that when you take determinant of L minus lambda 1 chopped, it's just the sum of lambda to the power m E k m of L. Right? So the claim is that this these elements are in the center, in the Poisson center of P K. So they'll commute, I claim that they commute with everything inside this angle. So you just, it means that before you take the rational, take the rational part, right? Before you chop it out, you work with just the algebra which is just the union of centers of S, P, K, N. So that's a kind of Gelfand-Zetlin algebra, right? And the proof is pretty simple. Proof of this claim. Consider differential operator dk equal to the composition of partial derivations along this anti-diagonal. D over d x1n, d over d x2n minus 1, and so on until you get to k n minus k plus 1, I think, right?
So only this part of the diagonal, yes?
Yeah, just along this part of the diagonal.
Which is in zeros.
Yeah.
Okay.
So this is operator from S GLN to S GLN, right? Just take this. And of course, dk is equal to dk minus 1, composed with d over xk n minus k plus 1. Okay, what is also evident? When you take dk and apply it to the coefficient of the original characteristic polynomial, m, k, j, let me j, l, you will end up in this symmetric algebra of p, k, n. And that's because every row and every column has only one element appearing in every monomial there. So all the other will be killed. Yeah. So that's evident. And now, in order to prove this claim, it is sufficient to prove the following lemma. From this observation, it follows that to prove this claim, the following lemma is sufficient. Take the operator d over d x k n minus k plus 1 and apply it to f from the center of p k minus 1n. Then this will commute with Poisson commute with any g from S p k n. Everything lies inside S GLN. And of course we take the Poisson bracket with respect to this S GLN. Okay, the proof of this lemma is now a kind of a variation in direction of the argument shift method. Something I haven't seen in the context of Toda system before, and that makes me a little bit curious whether it is just a slip of hand or whether there is actually some big theory underlying this. In any case, so we take the proof of this claim is very simple. You take d over dx k n minus k plus 1 and differentiate the commutator, which is of course 0, right? On the other hand, this will be equal to the commutator of d over dx k n minus k plus 1 of f with g plus f d over dx k of g, which is 0, just because g does not depend on this element. G is inside pk, so it doesn't depend on previous, right? All the k, the first k lines are non-existent in k, and the last k columns. Plus f and g with respect to the what they call the frozen argument Poisson bracket. I use this notation, and one can write down the expression for this Poisson bracket pretty straightforwardly here.
Recording in progress.
It is something like, so f and g k n minus k. So let me put it even better than that, just ij. I think it's sufficient to have ij here. It will look something like, up to the order, which I always forget, something like this. df, so the sum is over p, df over dxi p dg over dpj minus vice versa. df x pj, sorry, let's put dg x I p df over dx pj. Now, g does not depend on the elements which belong to the kth column or n minus k plus first, the kth row, or n minus k plus first column. So this is also 0. Very simple. And this means that this is 0. And we have this claim. Something very simple, remarkably simple. Now it is possible to prove, now the only thing which remains is to show that the ratios of E k m divided by E k 0 is invariant with respect to the action of B plus. And this is done also very easily with the help of this operator decay. You see, when you have an element B in, say, Lie group, I don't know, Lie group BK, Bn. And when you take B acting on, by conjugation, acting on dk of f, right? Let's put it this way, by conjugation on the argument. It is equal to dkb applied to fb, right? Now fb is invariant, so it's just f. But dk of b is easy to compute. So using the fact that since so the action of the Lie group on partial derivations, it can be identified with the action of the same group on a joint space of the Lie algebra. And one can show that this will be equal just to dk of f times certain character of B. Sorry. What f? This, I mean f. Sorry. This f is just I j of L. I forgot to say. We all began with the following. I have forgotten to say that the following is true. Take this equation. Well, I don't know, probably better, j, I, j of L. And differentiate it by apply decay to this. And it is easy to see that, so on the left, you will get just up to the sign, just the determinant of L minus lambda 1 chopped. Okay. And on the right, you'll have, so on the right, you will have chopping invariance. I mean, dk of ij will be equal to E kj.
Yes, simple.
Yeah, very simple. I don't know how it is really very simple. And now you can even show that this ratio will be invariant just because the character which shows up here. This character appears from decay, and it will be the same for all elements with the same k.
Character of Bn.
Yeah, character of B, character of Bn. So the action of B on this function will be by character. This is done just by the following observation. You first pull this inside. F is invariant, so F doesn't change at all. But decay changes in a very special way. It actually will have something. Well, I don't have time to prove to explain this, but actually you can do this by straightforward computation, and it is even it is not always so. But for F of the sort which we used, if F has the property that every monomial appearing in F has every column and every row appearing only once in it, in this case we have this property. You can even write down the explicit formula for this character, because this character will just appear from decay, and that's all. Nice. So we have this. So this is the first statement I was going to talk about here. And the second statement will be about the way you can find explicit solutions of the corresponding flows. So let me say a couple of words about the flows. There is a well-known construction which allows one to compute, to find the solution, more or less explicit solution of Toda flow in terms of so-called QR decomposition. It is known, I think it's just what they call the Gram-Schmidt orthogonalization procedure. It is known that every matrix, non-degenerate matrix I don't know, whatever, A, B, C, D, I don't know, X, can be decomposed in the form of upper triangular matrix and orthogonal matrix. So for every X in GLN, R is in upper triangular and Q is in special orthogonal. So actually lower triangular, sorry.
Doesn't matter.
Right. Then one can use this to solve the Toda system as follows. So suppose we want to find the solution of the Toda system. With the initial data equal to L0 when t is equal to 0, right? Then you can do the following thing. Take exponent t times L0 and decompose it into the product of R of t and Q of t. Then now differentiate this. So the claim is the flow Q of t L0 Q of t transposed will solve the Toda system. And the proof is very simple. So first of all, we differentiate this with respect to t. We get L0 times RQ, right, on the left. On the right we shall have r dot q plus r q dot. Okay.
Differentiate the
Yeah, differentiate with respect to t, this equation.
at any point.
Yeah, for any t. Now we multiply. Sorry, I think it's just wonder whether it's better to do it on the left or on the right. Just a moment. I think it's better to. Yeah, I think it's better to change the order. Sorry. Yeah. So first I multiplied by r minus first q L0 equal to r minus first r dot q plus q dot. And then I multiplied by q minus first, by q transposed, right? So it means that q L dot q transposed will be equal to r dot r minus first r dot plus q dot q minus q transposed. Yeah, nice. Now this is L, right?
This is L.
Right. Nice. And this is M of L, because you see, this is the antisymmetric part, and this is upper triangular part. And one can show that M of L is just the projection of L along the I think lower triangular part onto lower triangular part onto the yeah. So this is M of L. Nice. Okay. On the other hand, if we take so this is so L is equal to okay, nice. On the other hand, take M of L and L. Use this. It will be equal to Q dot Q transposed with Q L0 Q transposed. Right? So what is this? It is equal to so when we multiply it will be Q dot L0 Q transposed minus Q L Q transposed Q dot Q transposed. Sorry, excuse me. Now, due to the fact that this is equal to minus Q transpose dot, we have that this is equal just to Q dot L0 Q transposed plus Q L0 Q transpose dot. So that's precisely the derivation of Q L0 Q transposed. You see, that's the standard way. That's the standard thing which people know about the system. The claim is that the same is true for all flows of this form. Let me, so how much time do I have?
Well, 20 minutes.
Okay.
15 minutes or something like that.
Okay, nice. I think 15 minutes will be enough.
Okay.
So now the following is true. First of all, let L0 be the initial data. Of our flow. We can consider EK0 of L0. Just the denominator of this. It will be just the determinant of L chopped, L0 chopped. Right? On the other hand, we have the following observation. As I mentioned, the Hamilton vector field of every function f is equal to the projection of nabla of f. Take f equal to the determinant of L. Then nabla of f will have the following form. Nabla of determinant of L will have the following. It is a matrix, which when you apply to a vector v, it will be equal to the following determinant. Take the following matrix. 0 here, then you take v1, the components of vector v, vn. Take the basis vectors e1 through en, and here you just enter the matrix a11, a1n, an1, ann. Then the determinant, the number of determinant, the gradient of determinant, will be matrix of this form. The value of this matrix on this vector will be given by this formula. If you take instead of this, and the only difference you have will be that here you have lambda, right? So if you want to obtain nabla of E km of L, you do the following thing. You take the operator dk. It commutes with the operator nabla, because nabla is the operator with constant coefficients. And dk is the operator with constant coefficients. And apply it to nabla of that L minus 1 lambda 1. And in this way you see that what was true about the invariance of decay, with respect to the action of the upper triangular group, remains almost intact here. The only difference is that here you will have to change the operator nabla by operator b, by nabla b, right? Nice. I mean that if you take, so the following is true, b will be equal to this. That's what I wanted to say, right? So it is determined by this, by the degree m element in this matrix, the element which stands at degree m of lambda. Nice. Now we take this matrix, which you can obtain by this procedure, and apply it to L0. So L0, you obtain this matrix, which I denote by capital E, K, M, capital bold E of Km of L0. This is a matrix. And divided by E K0 of L0. This will be a rational function on L with values in matrices. Right? Take the exponent of E bold divided by E K0 times T. Decompose it into R of T times Q of T. And the claim is Q of L0, Q transposed of L0 is the solution of the flow associated with the function IKM. And the proof is almost the same as here. The only thing we need to modify is the following observation. Here, we need to observe that when B is in fact orthogonal, then its action on nabla is trivial. It's a little bit, I don't know how to put this. I mean, it's not just this, it's actually what we need to prove. We need to prove the following, that if Q is of the form 1, 1, 1, K times some orthogonal matrix 1, 1, 1, K times K times K times, then Q applied to this ratio of matrices will be equal to E Km of Q L0 Q transposed divided by E K0 Q L0 Q transposed. So this is done more or less in the same way explained here.
So you
I can put this Q inside the brackets. Yeah. So in case of the lower, it is almost evident. It is just the same thing.
Q of this form.
Yeah, for any Q of this form. And that's just because this decomposition will have this Q of this form. The Q in this decomposition will have this form.
Okay.
So this is a way you can solve these additional flows. So I think, I don't think it is worth to speak about details of the proof in this time, but actually the proof is more or less standard from, is very similar to what I have talked about earlier. we just use the following observation, that for every matrix B nabla of F B transposed is equal to nabla B F of yeah, I think it's better to put like this. Sorry. Nabla of F B L B transposed like this. Like this. Be equal to B nabla sorry, it was yeah, sorry, it's like this. It will be B transposed minus first nabla of F B transposed. So this B and this B corresponds to the action of B on nabla. And this FB is trivial because we have assumed that F is invariant with respect to the action of B. And if B is orthogonal, then this will be just equal to B. And this will be just equal to B minus first. So and that actually accounts for this kind of identity. And the condition concerning these and these areas spanned by units, by ones, is due to the fact that we need to preserve the action of decay. And this is, of course, so if B is of this form, that its action of decay is trivial. Now, to see that our Q will be of this sort is simple, just because the matrix, which depends on L0, will have this kind of property. It will be concentrated it will be zeros everywhere except for the k by k, except for n minus 2k times n minus 2k block in the middle. All right. So this matrix has this form. So when we exponentiate it, we shall have ones on this diagonal and zeros elsewhere. And that provides the condition we need. That's all, more or less.
Okay, thank you.
I'm sorry, but there are lots of things we can actually ask further. For instance, one can ask about the relation of these additional flows with coordinates on the symplectic leaves of the system. Now that we know how to solve these flows, how to find the solutions more or less explicitly, one can speak about the coordinates corresponding to them. One can further speak about other constructions of invariance of this sort. For instance, one can take, instead of taking the determinant of L, one can take some representation of L, for instance, and then take determinant of this representation and take the Chopin of this determinant. And in this way, one can obtain some new invariants which correspond to some other parabolic subgroups. For instance, in case n equal to 4, when you have n equal to 4, in addition to the standard parabolic subgroups which I told you about, yeah, to the subgroups of this sort, there is one more parabolic subgroup of this sort. Right? You can do this kind of step here. And one can find an invariant which will correspond to this parabolic subgroup, in the sense that its gradient flow will have this form. Will have the form 0, x minus x, 0, x minus x, 0, 0. So it will have this form. It will have two blocks of non-zero elements instead of one block, which we have in this case. And so on and so forth. There are lots of questions one can ask in this direction. And I really wonder whether something new can appear from these considerations. Okay. Now I think it's time to stop for me. It's time for me to stop.
Thank you, Гоша. А какой микрофон говорить надо? Любой?
Я могу вам отдать.
Thanks a lot. Questions, remarks.
Нужно распутать щепочку.
Сейчас скажу. Я думаю, не...
Вот так вот. Ну это...
Это невозможно. Questions, remarks. Okay. Then I wish you Merry Christmas and a Happy New Year, and we meet in February. Goodbye. Thank you. Кто выжил после этих испытаний?
В Zoom 3 человека, а остальные перешли на YouTube в какой-то момент. Zoom работал 80% времени, но...
Ну да, это, увы.
Ну, понятно, что это не самый комфортный способ.
Просто интересно, это как было, на самом деле, совсем непонятно или как вот хотя бы какая-то часть была. Мне, например, нравится эта конструкция с операторами D, я ее не видел.
Ну, я в какой-то момент уже перестал понимать просто от усталости. Я сегодня с самого утра пошел на работу.
Ну да, но сейчас уже поздно.
И там отсидел весь день. И как-то уже к концу сдулся. Но это есть в этом припринте
да,
все, да? Ага,
есть,
я посмотрю.
Там куча опечаток и таких. Потому что, повторяю, мы торопились это все выложить до праздников. Не знаю, это Диме нужно было до праздников. Я, честно говоря, я тоже хотел бы пораньше выложить. Но там, в принципе, серьезных опечаток нету. Серьезных. Там в паре мест есть такие опечатки, которые можно исправить. Ну и плюс там куча...
Ну, вы в журнал еще не отправляли?
Не. Нет, мы еще не отправляли, мы думаем отправить потом, но сначала нужно там все собрать какие-то рецензии у людей, которым это рассказываем, и так набраться смелости и нахальства, чтобы решить, куда отправлять.
Ну, количество смелости и нахальства зависит от того, куда вы собираетесь.
Вот я именно говорю, что вот мы будем смотреть, сколько у нас останется смелости и нахальства после обсуждения со всеми заинтересованными людьми. Если, значит, вообще была изначально там, поговаривали вообще о communications, я не знаю, это такая... Ну, в принципе, я считаю, что статья хорошая получается.
Почему?
Вот. Если никаких-то серьезных замечаний не будет, я, например, это показывал Решетихину статью, рассказывал ему об этих конструкциях. Он это так сдержанно, заинтересованно отреагировал. Вот. Ну, Николай Юрьевич, он такой человек немножко уклончивый, но в принципе так сдержанный интерес вроде проявил. Посмотрим.
Нет, Ну, а кто там из знакомых редакторов есть в Communications?
У нас никого.
Никого?
Ну, по крайней мере, я не помню. Там вроде... Мы когда-то раздавали с Юрой статью давно, нам даже публиковали, но я не помню, какой там был опыт, там, когда знакомый
Там,
редактор.
помню, покойный Дубровин был когда-то. Ну, поскольку он умер, то...
Да.
Так, Олег, а вы отнесли уже их компьютер, да? Вы отдали им компьютер?
Да.
Я пойду отнесу. Сейчас, а это как выключается?
Там что-то есть, вот тут не включайте. Ну, там если кто-то есть, там выключи.
Так, спасибо большое, с грехом пополам. Только я не могу выключить этот ваш приборчик.
Все, последний семинар был, да,
Да,
в этом году? Да.
Ага. Все, с наступающим.
С наступающим
Всего
вас тоже.
доброго.